Okay, so here I am on Project Euler.net, and I'm just going to be going through some problems here to keep my programming skills sharp. So the first problem is if we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. That is true. The sum of these multiples is 23. Find the sum of all the multiples of 3 or 5 below 1,000. So, one way to solve this problem would be by pen and paper, which Mr. Euler would have had to have done back in the day. He would have had to have listed out every multiple of 3 or 5 below 1,000 and then sum them together by hand, which would have, I don't know how long that would take. Would not be fun. But we have a computer at our disposal, and we have a programming language in which we can run a program that solves this problem for us. What we need to do is come up with a set of instructions or an algorithm that is the procedure for solving this problem. So that's what we're going to do next. Before we write any code, I'll be developing an algorithm for solving this problem.
So I've got a pen and paper out here where I'm gonna scribble out an algorithm for solving this problem. So as you can see, I've already got the word for there. I sort of started before recording. Basically, to solve this problem, we're gonna have to, for each number below 1,000, we're gonna have to test that number to see if it's a multiple of 3 or 5, and if so, remember that number and put it in a list. Once that's complete, once we have a list of multiples of 3 or 5 below 1,000, a list of numbers that are multiples of 3 or 5 below 1,000, we're going to sum all numbers in list. So that's the basic algorithm for solving this problem.
So here I am in my text editor, and as you can see, I've got some computer code written. Now I'll be using the Go computer language in order to solve these problems, because I want to learn a bit more about how to use Go, since it's a language that's sort of caught fire lately. So to stay on top of that, staying on top of which languages are pertinent, I will practice using Go. The first thing I can think that I'll want to do in this program, or what we're going to have to do, is repeatedly test numbers to see if they're multiples of 3 or 5. And that sounds like the perfect function to me. So we're going to create a procedure, a function, a method, whatever terminology you want to use to refer to this thing, to test whether a number is a multiple of 3 or 5. So I'm going to create a function is multiple of I don't know what the convention, if it's camel case in Go or if it's snake case. We'll just say, we'll just call it multiple 3. We'll have a function, so I'll work on this one first. So we know in the programming world, if you take a number and you divide it by 3 and there's no remainder after the result of that division, in other words the remainder is 0, we know that that number is a multiple of 3. If the remainder is anything other than 0, then that number is not a multiple of 3. So what we're going to do is accept an integer n here, which I do not know how to do in Go, so I'm going to go to the Go tour and divine how to accept define how to define a parameter. So let's go to this guy. Packages, variables, and functions. That sounds like what I need. So yeah. So in Go, you declare the name of the parameter first, and then the data type. So if we go back to my program, we'll have an int n or whatever, and we will say if n modulus 3 equals 0, return true, else return false. So we'll see if that's valid. I'll have to look up conditionals now. Flow control. If so there's brackets. I forget. Okay. So we use squiggly braces or brackets. And to test that this function works as expected, I will print the result of calling it on a multiple of 3. Multiple 3, 9 is a multiple of 3, so if we run this program, too many arguments to return. Oh, I forgot to specify that this returns a bool. Okay. let's try, so a multiple of 9 that returned true. Let's try a multiple 3 of 8, that should return false. And it did, so that's working. So I've got one function defined, and we'll define another. This time called multiple 5. Change this to a 5. And we'll create a third function, multiple 3, 4, 5. Return multiple 3, 4. So this, we're going to take the result of multiple 3, calling that function, and multiple 5. If either of those things are true for n, then it's a multiple of 3 or 5. Alright. So, here's where we implement our algorithm. So, the first part of the algorithm is for each number below 1,000. So, we're going to want to set up a loop. And we're looking at an example of that for, so we've got an example of that here. Just copy and paste it. So we have a variable I starts at 0, condition I less than 10, so the loop's going to iterate as long as that's true. But in our case, we need 1,000. So we're going to loop 1,000 times. Now, do the natural numbers include 0? 0 is... 3 is... Let's see. 0 divided by 3 is 0. Remainder 0. So, let's see. Natural numbers. I'm trying to figure out if 0 is a natural number or not, so I should just look it up. Okay, it doesn't say. Used for counting. So I'm guessing 0 does not count. Okay, so it can be 0 or... I suppose it doesn't matter. So I looked up whether or not 0 is a natural number, and it looks like it depends on how it's the natural numbers are being defined. But it doesn't matter, because if 0 is a multiple of 3 or 5, 0 gets added to the result, which doesn't change the result. So I guess we can start I at 0. Okay. So what we're going to want to do is, if, let's see, yeah, so we're going to have some and if I 5, if I is a multiple of 3 or 5, sum is going to get added. I is going to get added to the sum. And we're going to fmt dot print line. See if that works or not. Okay. So we create a variable called sum. We initialize it with the value 0. For every I less than 1,000, we check to see if that I is a multiple of 3 or 5. If it is, it gets added to the sum, and we just keep adding to the sum any numbers that are multiples of 3 or 5. So the answer that I got was 233,168. So let's check that answer and see if it worked. Alright, so how do I get an answer here? Project Euler answers. Numerical answers, alright. So if I look here, hey, I did it. So I successfully answered the Project Euler problem number 1. Which, I think the difficulty of this one is 5% or something. Difficulty rating, 5%. Yeah. But what I learned was how to write a simple for loop in Go, and yeah, how to declare and initialize a variable, how to declare and define a function, how to use an if statement. So those are all good things to learn. So on to problem number 2. Okay, so we're on to problem number 2. It says each new term in the Fibonacci sequence is generated by adding the previous 2 terms. By starting with 1 and 2, the first 10 terms will be 1, 2, 3, 5, 8, 13, 21, 35, 55, 89, and continue. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even-valued terms. So, that is our problem, and next step is to develop an algorithm to solve it.
So, my algorithm for solving this problem will be while Fibonacci and less than 4 million and if fib of n is even, add fib of n to a running sum. Okay, so there's my algorithm. Time to implement it in computer code.
Okay, so first thing we need to do is create a function that generates a number from the Fibonacci sequence. So I'll say func fib accepts an n, an int n, returns an int. And those of us who are familiar with computer science know we can use recursion to generate numbers from the Fibonacci sequence. So if n is equal to 1, you return 1. So if n equal to 2, return 2. And else, I'll just do it this way. Doesn't matter too much. Actually, it does. Okay, so just to be completely sure that we know what we're doing, I'm going to print Fibonacci 1 to see that it returns 1. It does. I'm going to print fib of 2 to see that it returns 2. It does. And let's try, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Let's try fib of 8. That should return 34. So let's see. Ooh, getting some infinite recursion going on. Which is not good. Okay, so let's look at this piece of code here. quite sure what's going wrong. I think I know. Alright, it's time to do some problem solving here. So, when I plug in Fibonacci of 8, that calls there we go. Alright. So, Fibonacci of 8 is the same as Fibonacci of 7 plus Fibonacci of 6. So that would be fib of n minus 1 plus fib of n minus 2. Okay. So now that I'm fairly confident that our Fibonacci function works, let's implement the rest of our algorithm. So, fib term for I for fib of fib term less than 4,000,000 6 zeros, and we need a way to determine if a number is even. Write a function for that. We'll continue to increment we'll see if there's plus plus in Go. Continue to increment fib term. If is even, so we got the result of a function call going in as the input of another function call. So we're getting sort of layered here. We need to add to a sum. Alright, so there's my little program to solve this problem, and we'll see if it works. Okay, so my result is 4,613,732. And we're going to check that answer. 4,613,732. Sweet. So that is Project Euler's problem number 2 solved. Okay, so here's problem number 3 of Project Euler. It says the prime factors of 130 or 13,195 are 5, 7, 13, and 29. What is the largest prime factor of the number, and I believe this is the number 600,851,475,143? I hope I'm pronouncing that correctly. So, we're going to come up with an algorithm for solving this problem, and we're going to implement it in code.
So the initial idea that I have an algorithm to solve this problem is the initial algorithm that I am thinking of is pretty brute force. It's not fancy or efficient or anything like that. What we're going to do is we're going to, for every n up to 600 billion 851,475,143. We're going to test if n is prime and n is a factor of the big number. I'm just going to refer to this 600 billion as the big number. Add that number to a list, then go through the list, find the greatest prime factor. Since that list will only be made up of prime factors. So there's my algorithm. Time to code it up.
So to begin with coding this algorithm, in my opinion, we're going to need a function prime, takes in an int, returns a bool, and a number is prime if its only factors are 1 in itself. So if there's any other factor other than 1 or itself that is present, then the number is not prime. So we can go for I. Okay. So here's what I'm doing. This is another algorithm for determining if a number is prime. So, one continual theme you'll see in computer programming is you have algorithms built on top of each other. So the algorithm for solving whether or not, or solving the largest prime factor of the biggest, or the big number, the algorithm for solving that depends on other algorithms, like algorithms that determine if a number is prime or not. So, just to test it out, let's see if we know that 5 is prime, so we'll check that out. Something's wrong with my for loop. Let's go. Oh, there's semicolons, okay. Just like any other loop in any other C-like language. Okay. What was I doing? It's building. And running. True, so 5 is prime, and 6 is not. There we go. Sweet. Another algorithm we need is whether or not a number is a factor of another number. Yeah, we can just call this func factor accepts an n, returns a bool, accepts 2. So this function will return true if x is a factor of y. To do that, we just need to do y modulus x equal 0. Okay. So we're going to, like our algorithm describes, for I, I'm going to start it at I'll start it at 2. I less than 600 billion, 856 million, 51 million, 475,143. Add to a list. You know, now that I'm thinking about it, we can probably simplify this algorithm by getting rid of this list idea and just keeping track of the largest factor so far. So I'm going to have another variable, largest factor, set it equal to 0. So if some number I is prime, and it's also a factor of the big number, and it's also greater than the largest factor, we're going to set the largest factor equal to I, because it's the largest factor so far. And then 50, largest factor. I should technically call this the largest prime factor. Okay. See how this works. Undefined largest factor. So there was a build error. And that is because of this. Alright. So, unfortunately, this algorithm that I've come up with is not very efficient. So, I'm sitting here waiting for the result of my program, and my program is still running, so I'm not quite sure if this algorithm is going to solve the problem before the sun explodes. Yeah, so if we look if we do some more analysis on my algorithm, right, we'll see that it's pretty bad in terms of time complexity. I've got a for loop iterating 600 billion times, which isn't in itself a bad thing. Computers can iterate through 600 billion items pretty quickly. But for every 6 billion items, for each one of those items, I am also iterating another 6 billion times, basically. So the time complexity of this algorithm is quadratic, which, if you look at it on a curve, if you were to draw the quadratic curve, you would see that as n increases, so does the number or the time it takes for this algorithm to complete. And for very large numbers of n, it's going to take a very, 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 very long time to compute the answer. So, the main issue that I see so technically this program I think solves the problem, but it doesn't solve it in a reasonable amount of time. So I'm going to have to use my brain to figure out how to make this algorithm more efficient. And maybe we can do that by increasing the efficiency of the prime algorithm. If I were to somehow make it so that we didn't need a for loop there, we didn't need to test every number to see if it was prime. We didn't need to test every number in between n to see if it was a factor. Yeah. How to know if a number is prime in an efficient way. It's a good question that I do not know the answer to at this point. Well, I'm going to have to come back to this one. I think I'm going to take a break and let the brain sort of subconsciously process this in the background, and hopefully when I come back to this with fresh eyes, I will have some idea about how to make this algorithm more efficient.